To determine the number of times you need to apply the chain rule, we need to see how many embedded functions there are. Okay, so I'm just going to go from inside out. So here's my 4x function. Okay, or so I'm going to just say 4x minus 1, I guess. That's one function. Okay, that's embedded inside a cube function. The cube function is embedded inside a sine function. Okay. And the sine function is embedded inside the log function. So we have 1, 2, 3, 4 functions that are embedded inside each other. So when I differentiate from outside in, I'm going to differentiate the log first. So I end up with sine, I'm just going to write like this, sine of 4x minus 1 cubed. Okay, so applying the derivatives of the sine, then we end up with times cosine of 4x minus 1 cubed. Okay. The next embedded function is a cube, so we end up with 3 times 4x minus 1. And then the most inside function is a 4x, so I times by 4. Okay, so there is my derivative. I can do some simplification here. There's a cotan function if you want to combine that as one function. I'm not going to bother. I'm just going to leave that as y prime is equal to 12 times 4x minus 1. And this is going to be cosine of 4x minus 1 cubed over sine of 4x minus 1 cubed. Okay, so if you want, you can combine that cosine over sine. Since the arguments are exactly the same, we can combine that into a cotan function if you like. Okay, so match the following graphs with their derivatives. So the key to matching the graph with the derivative is we want to look for where the derivatives are equal to 0, okay, the horizontal tangents. So I'm going to start with that cubic function, and I want to match up where the zeros are equal. So this one has the horizontal tangents in that point. The cubic function looks like a quadratic. I should test my positive negative slopes. So it's positive going here, positive in this region here, and it's going to be negative on the outsides, negative on the outsides. Yeah, those two definitely go together. For this next one, it looks like it is that slopes are constant and changing. So we have a constant positive and then abruptly, so the slope should jump to negative and then again jump back to positive. The only one that jumps is going to be this one here. Okay? And that will give us an indication that those two go together. For the next one here, we have a zero slope here. Well, that's got a zero slope in the middle, zero slope in the middle there. It crosses the x-axis at those points. It looks like it's going positive and leveling out to 0. Here it's positive and levels out to 0. This is negative and levels out to 0, so negative and leveling out to 0. That looks like the right one. If we compare it to this one here, first of all, that looks like a cubic function, so its antiderivative should be a quartic or fourth degree function. That's not true, so those don't seem to match. These have 3 zeros. This only has 1 point where it has a 0, so those ones cannot possibly match. So by default and by analysis, we can connect those two. And by default, these go together, but let's just check. But here we have 1, 2, 3 points of 0, so they have 1, 2, 3 corresponding points where the derivative crosses the x-axis. Here we have a fourth degree polynomial. This is a third degree polynomial. It seems to match the power rule. So we can be fairly confident those two are matching graphs as well.